So I really like to use balloons as models for orbitals, and that's because it really helps me to see them in 3 dimensions. Because in the textbooks we've got line drawings, and so sometimes people get in their heads that orbitals are flat when they're actually working in 3 dimensions. So if we take a ball or a simple single balloon, this is like an s orbital. So if we think this is our 1s orbital, as we go down a period in the periodic table, we start having 2s orbitals. So they're going to be bigger and higher in energy than the 1s orbitals. And then we move on to having 2p orbitals. And so we have a change of phase at the nucleus. And you can see we can orient them in different directions. So we'd have px, py, and pz. And then eventually in the 3rd period, we'd move on to having 3p orbitals, and these would be bigger than our 2p orbitals. But again, 3 dimensions can be oriented in our x, y, and z axis. And so it's really important to consider the radial extent of orbitals, because that affects how much shielding they do and how well their electrons can penetrate, how close they can get to the nucleus. So a 1s orbital, its electrons are going to be staying really close to the nucleus, whereas a 2s, where they're larger, you can imagine them kind of superimposed on top of each other, their electrons will spend some of their time at the nucleus but some of their time further away. So they're less good at shielding a 2s electron and they're less penetrating. But the 2s electrons will, this is going to be inside there, the 1s electrons will be inside, the 2s can penetrate within the space occupied by the 1s. Similarly, if we consider now, say, a 2p orbital, just got to get my prop here. If you think these are superimposed on a single nucleus where my fingers are, the 2p electrons, they have a node at the nucleus. So some of their time there's no chance of having an electron there. Whereas in the 2s, they can get really, really close to the nucleus, and they spend more of their time near the nucleus than in the 2p orbital, because in the 2p orbital, some of the time the electron's here or here or here, further away from the nucleus. So a 2p orbital is less shielding than a 2s or a 1s, but those electrons can penetrate the 2p electrons into the 2s and also into the 1s space. And so this is what shielding and penetration is about, and that's what affects our effective nuclear charge, how good electrons are at shielding and penetrating. Okay, on to the last topic for this short model video, polarizability. And we're going to talk about it more on the next slide. So polarizability is how easy it is to distort the electron cloud. So if we have a small, tightly held electron cloud close to the nucleus, so if we imagine a fluorine atom compared to an iodine atom, fluorine being very electronegative and the electrons in its valence orbitals experience a high effective nuclear charge, it's very hard to pull electrons away. Whereas in iodine, it has lots of orbitals, lots of very diffuse orbitals. It has electrons in 3p orbitals and so on. They're going to be much more easier to pull away from the nucleus because they're experiencing less of Z. They have a lower effective nuclear charge. And so what would attract electrons? Something that's a positive charge. So if we have something that's small and has a very positive charge like lithium plus or aluminum 3 plus, it's going to be trying to pull the electrons away. So we can think of it as pulling on the tail of the balloon and attracting those electrons. It's polarizing the electron cloud. But it's very hard to polarize the small electron cloud of fluorine, much more easy to polarize the big electron cloud of iodine. So the highly charged small atom or cation, positive charge, attracting the electrons. This is doing the polarizing. The atom which has the electrons and is soft, kind of fuzzy electron cloud, that's the thing that's being polarized, or we say it is polarizable. And more on that on the next slide, where we talk about polarizability and Fajion's rules.